Hi students, today's topic of discussion is heat capacity. What do you mean by heat capacity? That is, it is the capacity to get heated up. It is the capacity to get heated up. How do you come to know a substance has got heated up? That is, how do you come to know a substance has got heated up? Or how can you heat up a substance? It is by giving it heat. Or how will you come to know that substance is heated up? Okay, shall I ask one question? That is, how will you come to know that substance is heated up? That is, by measuring its temperature. Or how will you come to know that the substance is heated up? That is by measuring its temperature. There is an increase in temperature. Okay, that is, increase in temperature of a system is proportional to the heat transferred. That is, Q is equal to, that heat transferred is proportional to the increase in temperature of a system. Q is the heat transferred, then it is directly proportional to delta T. That is the temperature, increase in temperature of the system. To remove the proportionality sign, we are using here a coefficient, that is Q is equal to a coefficient into delta T. This coefficient C, we can denote it as C. That is, this coefficient C depends upon, that is, the magnitude of C depends on the size and composition and nature of the system. That is, this C, that is the heat capacity. This depends upon the size, composition and nature of the system. Okay. We can define heat capacity, that is, heat capacity of a system is defined as a quantity of heat required to raise the temperature of the system by 1 degree. That is, if Q is the amount of heat transferred, then it is equal to C into delta T. This delta T means rise in temperature, that is T2 minus T1, rise in temperature. And what is C? C is the heat capacity. And it depends on its magnitude depends upon the size, composition and nature of the system. Okay, that is, size means mass. This heat capacity is depending upon the size, composition, that is depending upon the mass. And can you tell me, heat capacity is an extensive or intensive property? It is an extensive property. Okay. Heat capacity is an extensive property. If the value of C is high, then what is the temperature value? The rise in temperature value will be low. If temperature value is high, then heat capacity is low. That is, these two, the product of these two make the value of heat energy. It's a fixed value. That is, we are giving a fixed amount of heat. Then the product of these two makes this value. Hence, when the heat capacity is increased, then rise in temperature will be lower. If the heat capacity is lower, then the rise in temperature will be higher. Okay. That is, in other words, we can say like this, that is, those substances which is having high heat capacity, if you are providing the same amount of heat to them, the temperature increases would be less. That is, those substances which is having high heat capacity, that is, those substances having high heat capacity, if you are providing the same amount of heat to them, the rise in temperature, the increase in temperature would be less. It is when specific heat capacity is increased, the rise in temperature will be lower. Okay. And those substance which is having low heat capacity, that is those substance which is having a low heat capacity, if you are providing the same amount of heat to them, what will happening here? That is the temperature would really go high. That is there is a rise in the temperature. The temperature will much more increase. The temperature would really go high. That is, it would increase much more. That is the product of C into delta T would be equal to the amount of heat that you gave. Okay, all of you got it. Let us discuss the value of heat capacities of different substances. Just go through the real life example. That is the value of heat capacity of different substances, that is sand and water. Let us take sand and water. Water has a very high heat capacity. That is, water has a very high heat capacity, which means you have to provide lot of heat to increase the temperature by 1 degree Celsius. That is, water has very high heat capacity, which means you have to provide lot of heat to increase the temperature by 1 degree Celsius. That is, during summer, when you go out into the beach, you love the water. Why? Because the water is cool. On the other hand, sand has low heat capacity. So, just by giving little heat, it suddenly get heated readily. In the nature, we can see the desert. There is sand in the desert during the summer. The sand in the desert is burning. Okay, that is sand, it has lower heat capacity and water has high heat capacity. Water has high heat capacity which means what? We have to provide a lot of heat to increase the temperature by 1 degree Celsius. Okay. Sand has lower heat capacity means what? That is, we have to provide very little amount of heat to increase the temperature by 1 degree Celsius. Okay. I explained all these things for the sake of knowledge and also to get the basic idea of heat capacity. Okay. That is, heat capacity of a system is defined as the quantity of heat required to raise the temperature of the system by 1 degree Celsius. Another two quantities are specific heat of the system and the molar heat capacity of the system. That is, if the mass of the system is 1 gram, if the mass of the system is 1 gram, the heat capacity is called specific heat capacity of the system. And if the mass of the system is 1 mole, then the heat capacity is termed as molar heat capacity. That is, specific heat capacity means it is a quantity of heat required to raise the temperature of the unit mass of a substance by 1 degree Celsius. Here mass is considered. That is, mass is fixed. That is, unit mass is taken. That is, if we are considering the unit mass. That is, specific heat capacity means it is a quantity of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius. That is 1 Kelvin, equal to 1 Kelvin. Okay, here mass is fixed. That is 1 gram. Okay. Then molar heat capacity means it is the quantity of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. It is the quantity of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. Here quantity, unit mass is fixed, that is 1 mole. You can write it as that is Cm, molar heat capacity, is equal to C by N, that is heat capacity by N. Okay, consider a system in which its temperature T1 is raised to T2 by absorbing a heat of Q. Then its heat capacity is given by the equation C is equal to Q by T2 minus T1, that is delta T. Okay. If you are considering a very small quantity of heat dQ, that is when small quantity of heat dQ is absorbed, we can write it as C is equal to, heat capacity is equal to dQ by dt. Okay. There are two types of heat capacity, that is molar heat capacity at constant volume and molar heat capacity at constant pressure, that is Cv and Cp. Since Q is not a state function, heat capacity C also is not a state function and depends upon the path followed. Okay, it's a path function. Hence, it depends upon whether the condition adopted for the change is constant volume or constant pressure. That is, this heat capacity is a path function and it depends upon the path followed. That is, it is depending upon whether the condition adopted for the change is constant volume or constant pressure. Hence, there are two types of molar heat capacity. There are two types of molar heat capacity, that is molar heat capacity at constant volume and molar heat capacity at constant pressure, Cv and Cp. First, we are discussing molar heat capacity at constant volume, that is Cv. Okay, that is, we know that C is equal to dQ by dt. You can put it as equation number 1. So, according to first law of thermodynamics, we have dQ is equal to du plus pdv. Okay, can put it as equation number 2. 2 in 1, that is 2 in 1. We are putting this equation in 1 implies that is C is equal to dQ by dt, that is we are substituting for dQ this term du plus pdv by dt. Put it as equation number 3. And then at constant volume, here we are considering at constant volume, heat capacity at constant volume. So this condition is applying here. At constant volume, what is happening? That is dV is equal to 0. dV is equal to 0. Then equation 3 becomes what? Cv, that is heat capacity at constant volume, equal to dou U by dou T, that is this term becomes 0 at constant volume. There is a molar heat capacity at constant volume of a system is equal to the rate of change of internal energy of the system with temperature at constant volume. It is molar heat capacity at constant volume of a substance is equal to the rate of change of internal energy of the system with temperature at constant volume. That is, it is the internal energy change of the system for 1 degree rise of temperature at constant volume. Molar heat capacity at constant pressure, that is Cp. Let us derive the equation for Cp. C is equal to dq by dt, that is du plus pdv. For this we are substituting du plus pdv, okay, by dt. Then heat capacity at constant pressure Cp is equal to what? Dou u by dou t at constant pressure plus, that is here pressure is constant, taking outside, and P into dou V by dou T at constant pressure. Okay, this is the equation number 1. Now next, we have already know that what is the enthalpy equation of enthalpy. X is equal to U plus PV. Can put it as equation number 2. That is differentiating this equation 2. We are differentiating this equation 2 with respect to temperature at constant pressure. It is dou H by dou T at constant pressure. That is differentiating this equation 2 with respect to temperature at constant pressure. Is equal to dou U by dou T at constant pressure plus P into dou V by dou T at constant pressure. This is equation number 3. This dou H by dou T P, dou U by dou T P. That is differentiating with respect to temperature at constant pressure. P is a constant here, hence P taking outside, and dou V by dou T P. This is equation number 3. From 1 and 3, from equation 1 and 3, we have Cp is equal to what? Dou H by dou Tp. Okay, this is equation for Cp, that is molar heat capacity at constant pressure. Molar heat capacity at constant pressure of a system is equal to the rate of change of enthalpy of a system with respect to temperature at constant pressure. That is, it is the enthalpy change of the system for 1 degree rise of a temperature at constant pressure. Okay. Here is the notes for molar heat capacity at constant volume and molar heat capacity at constant pressure.